Welcome back to the Deep Dive. This is where we take complex, often really dense technical source material, and we transform it into pure, focused knowledge for you. If you're prepping for a big project, maybe you're trying to get up to speed in a new field, or you're just driven by that intense curiosity, we call you the learner, then you are definitely in the right place. Today, we are pulling back the curtain on something that is just fundamental to everything we build. We're talking about manufacturing precision, and specifically, we're diving deep into the world of tapping. Now, this isn't just about, screwing a bolt into a hole. This is about the highly engineered process of creating reliable, load-bearing threads.
The kind that hold aircraft together.
Exactly. They keep turbines spinning. They ensure the structural integrity of your car. It's everywhere.
It really is the silent hero of engineering, isn't it? I mean, a thread is basically a tiny, incredibly complex helical ramp.
A ramp, I like that.
Yeah, and it's designed to manage these massive physical forces. If that tiny ramp fails, the entire assembly can fail. So our mission today is to dig into the technical materials. We're talking tooling catalogs, process guides, the physics behind it all, and to give you the essential shortcut.
Okay.
We want you to understand the theory, the tools, the really precise calculations, and all the execution parameters that guarantee a successful, strong thread every single time.
All right, let's unpack this right away, because the entire world of tapping is really defined by one core crucial conflict.
It is.
We have to draw a really hard line between cutting a thread and forming a thread. Everything that follows, your tool, choice, machine torque, and especially the pre-drill size, it all depends on this one distinction.
Absolutely. Think of it as two completely competing approaches to material science. A traditional method, that's using a cutting tap.
Okay.
And this works just like any other machining process you can think of. It cuts the material, it shears it away layer by layer, and it generates chips.
So it's removing metal.
It's removing metal to create that negative space, the groove of the thread. It requires less machine power, which is a plus, but it creates a waste product, the chip, and that chip has to be managed.
And then the alternative, the forming tap. This is what's called the chip-free solution, right?
Yep. It's fundamentally different. A forming tap doesn't remove any material. It deforms it or displaces it. It's a cold working process.
So like pushing it out of the way.
Exactly. Imagine rolling clay with a threaded rod. You're not cutting the clay, you're just pushing the material out of the way and forcing it to flow into the shape you need.
And that eliminates the chip problem.
Completely. Which is a massive benefit, especially in deep blind holes or when you're working with difficult stringy materials.
Okay, so if forming taps eliminate chips, they sound, inherently better. But that high torque requirement you mentioned, that has to be the trade-off. What exactly are we gaining and losing when we choose to deform material instead of remove it?
And that's where the physics gets really interesting. You are paying a high price in required machine power. I mean, you are physically reshaping dense material.
Right.
That requires significantly higher torque. We're talking often 30 to 50% more, depending on how malleable the material is.
But the payoff must be worth it.
The payoff is huge, especially when you're working with ductile materials like aluminum, certain types of stainless steel, and soft carbon steels.
So tell us more about that payoff. Why is the thread actually stronger when it's formed?
It really comes down to two things: work hardening and grain structure.
Okay.
When you use a cutting tap, you're literally slicing across the material's grain structure, which can sometimes weaken the flank of the thread.
But with a forming tap?
With a forming tap, the material is compressed and forced to flow. You're essentially work hardening the surface as you create it. This compression leaves behind what's called residual compressive stress, which dramatically improves the thread's fatigue life and its overall strength.
And the grain structure flows with it.
Precisely. The material's grain structure flows smoothly around the new thread shape, making the final product incredibly robust. For critical components where thread fatigue is a major risk, forming is often the undisputed champion.
Provided the material is ductile enough to flow, of course.
That's the key. You have to match the process to the material.
That sets up our foundational conflict perfectly. Cutting versus forming. Now, before we can even think about putting a tool in a machine, we need to understand exactly what that tool is made of. We have to speak the language of precision. Any tap, whether it's cutting or forming, is a complex piece of geometry. So let's dedicate a moment to the specific terminology that dictates its performance.
You have to. In manufacturing, communication is precision. There are 8 defined features that really dictate how a tap performs, how it engages with the material, and ultimately its life expectancy.
And just listing them doesn't really do it justice. We need to know what they do. So let's start with the core engagement features. We've got the rake angle, the relief or clearance, the chamfer angle, and the chamfer length.
Then you have the features that are all about chip management. That's the spiral point angle and the spiral angle.
And finally, the basic thread specs. The pitch, that's the helical distance between the threads, and of course the outer diameter.
Let's hone in on two that have the most direct impact on the cutting force and the chip formation. That's the rake angle and the chamfer.
Okay, the rake angle.
The rake angle is critical. It dictates how efficiently the material is sheared away. A higher, more positive rake angle usually means easier cutting and lower torque.
But it weakens the cutting edge.
It can, yes. Conversely, a negative rake angle gives you a much stronger cutting edge, but it requires more force. You'll often see that used for harder, more abrasive materials.
So just by changing that one angle, you're changing the shape of the chip and how much power the machine needs to draw.
Exactly.
What about the chamfer? The source material really highlights the chamfer length as being pivotal. Why is that?
The chamfer is essentially the entry ramp for the tap. It's that tapered section right at the tip, and its length determines how many teeth are actually engaged in the cutting process at the same time.
So it's about load distribution.
It's all about load distribution. A very short chamfer means all that cutting force is concentrated on just a couple of threads.
Which is aggressive.
Very aggressive. It gives you a great initial bite, which you sometimes need for materials that want to push the tool away, but it puts immense stress on those few teeth and can really shorten the tool's life.
And so a longer chamfer does the opposite.
A longer chamfer, which is often called a medium or a plug chamfer, distributes that load over many more threads.
Which is gentler on the tool.
Much gentler. It leads to a smoother engagement, better stability, and significantly longer tool life. The only trade-off is that it requires a bit more thread depth before the tap can really start working.
And that's why the medium chamfer is the standard for tough conditions.
Exactly, like those handled by a spiral point tap. Getting the right chamfer length is a direct negotiation between, the durability of your tool and the required tapping depth.
So we've defined the internal parts of the tool, but these things don't exist in a vacuum. They have to interface with machine tools all over the world.
Mm-hmm.
And that brings us to the alphabet soup of standards: DIN, ISO, and ANSI. If you're running a global manufacturing operation, this is where the setup headaches really begin.
Oh, this is a failure point that is hiding in plain sight. These standards, they define the physical geometry of the tool, specifically its overall length and its shank diameter.
And they are not interchangeable.
They're not interchangeable in a high-precision CNC environment. If you grab the wrong standard tool for your specific holder, you introduce runout, and that instantly ruins the thread.
Okay, let's break these down one by one. We'll start with DIN, the German standard.
So DIN tools are generally characterized by a long overall length, or OAL, and they rely entirely on metric measurements. You'll often see them preferred for deep reach or specialized operations where you just need that extra length.
Then we move on to ISO and ANSI. They look similar on paper,
Very similar.
but they differ critically at that interface point, the shank.
Exactly. Both ISO and ANSI generally have a pretty short overall length, which makes them compact. They're often preferred for high-speed applications where you want to minimize tool stick-out to reduce vibration.
But the big difference is the shank diameter.
That is the major, unforgivable distinction. ISO, being the global standard, it naturally uses metric shank diameters. ANSI, the American standard, uses inch measurements.
And why is this so critical for the listener? I mean, if I try to put a 10 millimeter ISO shank into a 3/8 inch ANSI holder, what actually happens?
That slight mismatch, that difference between metric and imperial dimensions, it might only be a few hundredths of a millimeter.
But that's enough.
It's more than enough to cause severe runout. And runout just means the tap is rotating eccentrically instead of perfectly on its axis.
Which translates directly into a bad thread.
A bad thread, rapid tool wear, and chatter. That's that terrible vibration that not only ruins the part but can actually damage the machine spindle over time. You have to match the standard to the holder, period.
And just to make things more complicated, there's a hybrid, the Dynancy mix.
Right. This is a practical compromise, really. It's usually driven by what machines a shop has or their existing tool inventories.
So what does it mix and match?
The hybrid tool typically adopts the shank diameter from the ANSI inch standard, so it's compatible with all those widely available American-style holders, but it keeps the overall length from the DEN standard.
Ah, so you get the reach of a DIN tool with the mounting of an ANSI system.
Precisely. And awareness of this is crucial because if you assume the overall length based on the shank type, you can end up with a collision or a depth error in your program.
Okay, with the vocabulary down and the global standards addressed, let's get into the selection process. The geometry of the tap has to match the geometry of the hole and the characteristics of the material.
Mm-hmm.
And this entire section seems to be dictated by one crucial concept: chip management.
Where are the chips going?
That's the question.
That is the single deciding factor. Tapping, at its core, is a chip evacuation problem. If you don't get the chips out of the way, they jam up, they pack the flutes, torque goes through the roof, and you usually snap the tap.
So let's start with the easy scenario, through holes. The chips can be pushed right out the bottom. For this, we're using the spiral point tap.
The spiral point tap, which a lot of people call a gun tap, it's ingeniously designed. It has straight flutes, but right at the cutting face.
That's where the magic happens.
Exactly. The flutes are ground at an angle, the spiral point angle, and it acts like a little scoop, aggressively pushing the chips forward and down through the hole.
And because the chips are evacuated ahead of the tool, you don't need deep flutes along the whole tap.
Right. Which makes this style the strongest tap available. It has the largest core diameter.
So because it's stronger, it's better suited for tough conditions.
Precisely. It can handle higher cutting loads, and it's the most common tool for high-volume through-hole tapping. That medium chamfer we talked about, distributing the load over several threads, that's the typical pairing for this robust push-style tool. It is the benchmark for high efficiency in through-hole machining.
Okay, now let's flip the script. We go to the most common scenario, which is the blind hole. A hole that stops. You can't push the chips forward.
So you have to pull them backward.
And this demands the spiral flute tap.
The spiral flute tap is the most ubiquitous tap style overall for a reason. Its flutes are helical, kind of like a drill bit. As the tap turns, that helix acts like an auger and drives the chips up along the shank and out of the hole.
Which prevents that chip packing at the bottom.
Which, in a blind hole, is a death sentence for the tap. The degree of that spiral angle can be calibrated based on the material, but the fundamental job is always the same. Lift the chips out against gravity and the flow of coolant.
Okay, so spiral point for pushing, spiral flute for pulling. But what if the chips themselves are the variable? That brings us to the straight flute tap.
The straight flute tap is a specialist's tool for specialist materials. It has no spiral, no point angle designed to direct the chips.
Which sounds like a problem.
It sounds like it, but it works wonderfully for materials that naturally break into very small, short, brittle chips. Think cast iron, bronze, or certain hard plastics.
Ah, so because the chips are small and don't tangle up.
They just fall easily into those straight flutes and can be evacuated without jamming. You don't need the complex geometry to manage them.
This sounds like a high-volume, very cost-effective solution in the right environment.
It absolutely is. The source materials confirm it's used heavily in the automotive industry, particularly in casting applications.
Engine blocks, pumps, valves.
Exactly, where cast iron is the norm. It's highly versatile and can be used for all holes and depths, but its competitive advantage is really maximized when you're dealing with those short chipping materials that don't need a spiral.
And finally, let's circle back to the forming tap. We established it's chip-free, but what dictates if a material can be formed versus having to be cut?
The material must be ductile. That's the key. It has to be able to deform plastically without cracking.
So we're talking soft steels, some stainless steels, aluminum.
Right. The material properties are everything. If the material is too hard or too brittle and you try to form it, you'll just shatter the tap and ruin the part. But when the material is right, the benefits are incredibly compelling.
We mentioned the strength increase earlier. Let's linger on that for just a second because this is a deep dive. Why would I choose a forming tap over a cutting tap for a critical aluminum part?
Okay, so imagine the forces acting on a screw thread. They're all concentrated right at the root of the thread.
Right at the weakest point.
Exactly. Because the forming process compresses the metal, it actually creates a denser, tougher thread structure that is often, 10 to 30% stronger than a cut thread in the same material.
And you get a better surface finish, too.
A much better, smoother surface finish. Since there are no chips, there are no thermal issues tied to chip removal or friction. And the quality and longevity of a formed thread in a ductile material just far surpass that of a cut thread. It really is a high-performance solution, even if the machine has to work a little harder to get there.
Okay, we have chosen our tool based on the material and the hole type. Now we hit the technical bottleneck. This is where most failures happen. The critical calculation. If you miss this step, Your perfect tool, your perfect machine, your perfect coolant setup, it's all irrelevant. The pre-drill hole diameter, what we're calling D, is the single most crucial variable for a good thread.
This is non-negotiable. And it's the single greatest aha moment for anyone getting into high-precision tapping. The difference in the calculation for a cutting tap versus a forming tap is subtle on paper, but it's catastrophic if you confuse them.
Get the whole size wrong.
And you either don't create a full thread or you overlay the tool and break it. It's one or the other.
Let's slow down and walk through this step by step.
Okay.
Let's start with the simpler one. Calculating hole size for cutting taps.
Okay. Since a cutting tap is designed to remove material to create the full thread shape, the initial hole has to be smaller than the final thread diameter.
And it has to be smaller by exactly the amount of material that needs to be cut away.
Right. And the formula reflects that. It's D equals TD minus TP.
So hole diameter equals the nominal thread diameter minus the thread pitch.
Let's run a metric example. It's clean. It's easy to follow. We need an M10 thread with a standard pitch of 1.5 millimeters. So an M10 by 1.5.
Okay, so the nominal thread diameter, TD, is 10 millimeters. The pitch, TP, is 1.5 millimeters.
It's simple subtraction. 10 minus 1.5.
Which gives us 8.5 millimeters for the required pre-drilled hole size. The material left for the tap to cut is exactly equal to the pitch.
Standard textbook machining practice.
Now everyone, hold that 8.5 millimeter number in your head, because when we switch to forming taps, the logic completely flips.
This is where we see so many errors on the shop floor. Because forming taps displace material instead of removing it, they need a significantly larger pre-drilled hole.
Because you need somewhere for that displaced material to go.
Exactly. If the hole is too small, you're trying to stuff too much material into the thread valleys. That leads to an exponential spike in torque and almost certain tool breakage.
So how do we figure out the right amount of space for that displaced material? What's the formula?
The formula is D equals TD minus half of TP.
Okay, so hole diameter equals nominal thread diameter minus half the thread pitch.
Right. We only need to account for half the pitch because the material is being displaced outward from the center to form the crests of the thread.
Let's go back to our M10 by 1.5 example. Nominal diameter is 10 millimeter. Pitch is 1.5 millimeters, so half the pitch is 0.75 millimeters.
So the calculation is 10 minus 0.75.
Which gives us a required hole size of 9.25 millimeters.
And now you see it.
That's a dramatic difference. 8.5 millimeters for the cutting tap, but 9.25 for the forming tap. That 0.75 millimeter difference in the initial hole size is the difference between a perfect, strong thread and a catastrophic failure.
And this isn't just theory. If a machinist accidentally used that 8.5 millimeter hole size with a forming tap, they'd be trying to displace almost double the necessary volume of material. The machine would alarm out, torque would skyrocket, and the tap would likely shatter inside the part.
Which is a very, very expensive mistake.
Especially on a high-value component, yes.
And the sources give us a great contrast using imperial units, which can be a bit less intuitive. For a 1/4 inch 20 thread, that's 20 threads per inch, the pitch is 1/20th of an inch, or 50 thousandths.
Right. So using the formula for a cutting tap, the hole size is about 0.2008 inches. The tap has to remove the material equal to that full pitch.
But for the exact same thread using a forming tap, the required hole size jumps up to 0.2264 inches.
It's a huge difference.
It just demonstrates that using the specific calculation for the specific process cutting or forming is the absolute gatekeeper to success.
And we really should mention tolerances. Tapping is rarely done at 100% thread height, especially in softer materials.
Why is that?
Because getting to 100% thread height is incredibly difficult. It requires massive torque, and the returns in strength diminish very quickly after about 75%.
So most industrial standards aim for what, 60 to 75%?
Exactly. And that variation is often accounted for by slightly adjusting that pre-drill diameter, D, within very tightly controlled tolerances. You're trying to maximize tool life without sacrificing essential strength.
Which means the drill bit you use has to be extremely accurate too,
Yeah.
and you have to watch it for wear.
The whole process is a chain of precision. One weak link breaks the whole thing.
Okay, so the calculation is done, the correctly sized hole is drilled. We're now moving to the physical execution, which demands perfect process management. And nothing is more central to that than the flow state, specifically coolant management. We have to shift from seeing coolant as just, a fluid to keep things cool. We have to see it as an essential active participant in the process.
It is the unsung hero that makes high-speed machining possible. The sources confirm there are three critical ways coolant influences tapping success, and they go way beyond just temperature control.
First on the list, chip evacuation.
In a cutting process, especially with those long chipping materials, coolant acts like a hydraulic force.
Yeah.
It physically flushes the chips out of the flutes.
And if they aren't evacuated,
They get recut, they gall the thread surface, and they increase the friction coefficient dramatically. Tool life just plummets.
second function, thread quality.
Right. Proper cooling prevents thermal expansion. If the tap or the workpiece gets too hot, the dimensions shift. That can lead to a phenomenon called galling, where little particles of the workpiece material actually weld themselves to the tap.
Which would tear up the thread profile.
It completely destroys it, rendering the part useless. Coolant ensures dimensional stability and a pristine finish.
And number 3 is tool life.
A tap that's operating at its maximum thermal load just wears out exponentially faster. Coolant reduces friction, it lubricates the cut, and it vastly extends the lifespan of what can be a very expensive precision tool.
So how do we get this crucial fluid to the point of action? We have 2 main delivery methods, external and internal. External is the oldest and most common, but it has its limits.
Yeah, external supply, usually through some adjustable nozzles pointed at the tool, can be successful when your chip formation is optimal, short, manageable chips, or for very shallow threads.
What's the best practice for that?
The recommendation is to use at least one, preferably two, coolant nozzles directed as closely as possible to the tool axis. Proximity is key because surface tension and the speed of rotation can just deflect the coolant spray, stopping it from getting deep into the hole where it's needed most.
But as soon as we're dealing with deeper threads or those long chipping materials, internal supply becomes non-negotiable.
Internal coolant supply, where the fluid is fed directly through microchannels inside the tap and exits right at the cutting edge, is always the preferred method.
Especially for things like stainless steel.
Oh yeah. For materials that produce those long, stringy chips, like certain alloy steels or stainless, internal coolant is the only reliable way to break those chips and flush them out.
And the source material is pretty definitive on depth, right?
It is. If you're threading deeper holes, say 2 to 3 times the diameter, internal coolant is highly recommended. For any depths over 3 times the diameter, it should be considered mandatory to ensure proper chip evacuation and lubrication.
But this high-pressure delivery system, it's not cheap to implement.
Yeah.
So that brings up the real-world dilemma. If internal coolant is so much better, why doesn't every shop use it all the time? What are the practical trade-offs?
It's cost and complexity. Internal coolant systems require specialized spindles, rotary joints, high-pressure pumps, often running at 1,000 psi or more, and of course, specialized, more expensive taps that have those internal channels.
So for a small shop doing simple shallow tapping in aluminum,
The economic benefit rarely justifies the capital investment. External coolant is the cost-effective workhorse. Internal coolant is the premium solution for challenging, deep, or high-volume jobs, where the cost of a single failure far outweighs the cost of the sophisticated system.
and what fluid are we actually pushing through these systems? What are the options?
We have several major chemical alternatives. The 3 most common are mineral oil-based coolants, synthetic coolant, and straight oil.
And there are a couple others.
Right. We also see vegetable oil-based coolants, which are gaining ground for environmental reasons, and semi-synthetic fluids, which sort of bridge the gap between oil-based lubrication and the cooling efficiency of synthetics.
Is one just better than the others across the board?
No, it depends entirely on the material and the operation. Straight oils, for instance, offer superior lubrication, which is fantastic for tough, high-friction materials like stainless steel. But they're not great at dissipating heat, and they can be messy.
And synthetics are the opposite.
Exactly. Synthetics are excellent at heat rejection, but offer less lubrication. The critical takeaway here, which our sources really stress, is that operators must always be acutely aware of the type of cutting fluid they're using and its oil content.
Because tapping stainless steel with a high water content synthetic
Is basically inviting galling and tap breakage. You have to match the fluid's lubricity to the material's demand.
We've reached the final layer of complexity, holding the tap itself. We have our perfectly designed tool, our perfect calculation, our perfect coolant flow. But if the tool holding device doesn't accurately sync the tool's movement with the machine's movement, the thread is ruined. And this is where we really see the split between older, mechanically compensated systems and modern, digitally synchronized CNC environments.
It is. The choice of tool holder is effectively a choice about how much intelligence and compensation you want in the machine's control versus in the tool holder itself.
Let's start with the more forgiving approach,
Mm.
the tension compression tapping chucks. People often call these floating chucks.
And they're designed specifically to compensate for feed errors. In older machines, or even modern machines running at low tolerances, the spindle speed and the axis movement might not perfectly align with the tap's pitch.
So the machine might be pushing too fast or pulling too slow.
Exactly. And if that happens, the floating chuck, which uses springs or some other internal cushion, absorbs that mismatch. It provides tension if the machine is running too slow, or compression if it's running too fast, to mechanically eliminate that feed error.
And we see this capability built into things like the floating rubber collet chuck.
Correct. The rubber collets can cover a wide clamping range, and that tension and compression capability ensures that the tap is always following its own thread path, no matter what minor inconsistencies the machine has.
We also see the quick change tapping chuck in this category.
The quick change system is all about versatility and speed of tool changes, which is great for low volume or varied production runs, but crucially, it also has that tension and compression mechanism.
So its main purpose is for older, less stable machines.
Or just general purpose tapping where absolute synchronization can't be relied upon. That floating mechanism acts as a kind of mechanical insurance against poor CNC control or backlash in the machine's mechanics.
But as machine tools get more and more sophisticated, the industry has moved away from that mechanical forgiveness and toward absolute digital precision. And that's the rigid tapping approach.
Rigid tapping uses a stiff holder, like a standard ER collet chuck, which offers zero compensation, none. The tap is held rigidly.
Which means the machine has to be perfect.
The motion of the spindle and the axis movement have to be perfectly synchronized by the CNC controller. That controller has to execute thousands of precise coordinated steps every second to ensure that the Z-axis feed rate exactly matches the pitch of the thread being cut.
So why go rigid if it removes that safety net of the floating chuck? What are the benefits?
Speed, cost, and accuracy. Rigid tapping is often much faster because you eliminate the mechanical lag of that floating mechanism. The holders are simpler, they're cheaper, and they're more compact.
And more accurate.
And most importantly, without that slight movement you get in floating chucks, you can achieve a more accurate thread pitch and depth. It's the highest speed, lowest cost approach if you have a very sophisticated, well-maintained machine.
But the sources issue a pretty severe operational warning about rigid tapping. If there's no compensation, what happens to tool life and, critically, the reversal speed?
The forces on the tap are dramatically increased. Every tiny error, every bit of resistance is immediately transmitted right back to the cutting edge and the machine spindle. This reduces tool life. But the real danger is in high-speed reversal.
At the bottom of a blind hole.
Exactly. When a tap reaches the bottom, the spindle has to instantly stop, reverse direction, and then feed back out precisely along the path it just cut. At high speeds, we're talking 4, 5, 6,000 RPM. The machine's inertia and the controller's latency mean that reversal is not instantaneous.
So for a split second, there's a conflict.
For a fraction of a second, the tap might still be trying to feed in while the spindle is trying to reverse, or vice versa. This lack of rapid reversal capability at high speed puts immense stress on the tap, and it often leads to catastrophic breakage.
So that limits the practical speed of rigid tapping, even on the best machines.
It does, especially when you're dealing with certain materials or depths.
So we have the fast, rigid approach that risks breakage and the slow floating approach that sacrifices some accuracy. And that brings us to the pinnacle of tool holding today. The synchronous feed tap chuck, it tries to bridge that gap.
This is the state-of-the-art solution. It's the first choice for high-volume, high-precision, synchronized CNC operations. It works essentially like a rigid tap holder.
But with a trick.
But it incorporates a mechanism for microfloat compensation.
How small is micro here? What is it compensating for?
It's tiny. We're talking just a few tenths of a millimeter. It's not there to compensate for major feed errors like the old floating chucks. It's there solely to account for the minute differences between the machine controller's digital synchronization and the physical reality of the tap's actual pitch.
So it's basically correcting for digital to analog error.
You could think of it that way. It's used primarily to eliminate the oversized threading that can sometimes happen under full rigid tapping conditions.
That sounds incredibly clever. What are the engineering benefits?
By allowing that tiny bit of float, the system reduces the thrust force on the tap flanks during cutting, which directly increases tool life compared to standard rigid tapping.
But it's still accurate.
Because the compensation is so limited, it maintains the precise depth accuracy you expect from rigid tapping. And furthermore, These advanced systems are designed from the ground up to handle high-pressure internal coolant. They're the complete package for a modern machining center.
It's fascinating. To get a simple, perfectly accurate hole at high speed, we had to invent a piece of mechanical hardware that works in perfect, micro-compensated harmony with an incredibly complex digital control system.
That's modern manufacturing in a nutshell.
This has been a necessary and, I think, a really deep dive into the engineering demands of precision tapping. We started with the choice of the material process and ended with the sophistication of the machine holding it. For our learner, let's synthesize the core, actionable takeaways from all the source material we reviewed today.
Okay. The first and the most foundational takeaway is that the distinction between cutting and forming is everything. It defines your tool, your material choice, and most critically, your pre-drill calculation.
You have to know which formula to use.
You have to know if you're using D equals TD minus TP for cutting, or D equals TD minus half of TP for forming. Miscalculating this by even half a pitch leads to expensive, immediate failure.
Okay, takeaway number 2. Chip management dictates your tool geometry. Your destination determines your tap.
Right, spiral point if you can push the chips forward in a through hole.
Spiral flute if you have to pull the chips back up out of a blind hole.
And if your material, like cast iron, breaks into nice small chips, the straight flute tap offers a robust, efficient alternative.
Third, never underestimate coolant. It is non-negotiable for tool life, for lubrication, for getting those chips out of the way.
And for deeper threads, we'll define that as anything 3 times the diameter or more. The investment in an internal coolant supply system is necessary to guarantee quality and to avoid breaking tools. And you have to match your cutting fluid's lubricity to the material you're working with.
And finally, the choice of your tool holder is intrinsically linked to the sophistication of your machine. The pursuit of high speed and accuracy demands that transition from the forgiving floating chucks toward rigid tapping.
But the operational risks of rigid tapping's reversal speed mean that the highest tier of precision manufacturing now relies on that synchronous feed tap chuck with its micro-compensation to combine speed, accuracy, and tool longevity.
The entire process really is a perfect illustration of applied engineering. You're balancing fundamental physics against extreme digital precision.
Absolutely. To get one simple, reliable, threaded hole, you have to balance the physics of generating a chip versus deforming material. You have to optimize the flow state of your lubrication, and you have to execute digital synchronization that demands tenths of a millimeter accuracy.
It really is incredible. The next time you encounter a crucial bolt or a screw maybe on a bridge, in a piece of medical equipment, or even just holding the wheel on your car, consider the engineering that went into that simple hole. Consider the complexity that was required to prevent one small miscalculation in a pre-drill size or one moment of machine lag from resulting in a weak thread that could cause a catastrophic failure down the line. Every single bolt and every hole you encounter is a testament to the fact that achieving simplicity and function often requires staggering complexity and execution.
A powerful reminder that precision is hidden in plain sight.
Thank you for joining us for the deep dive. We'll see you next time.